Everyone falls in love sometimes. Sometimes it's wrong, and sometimes it's right. For every win, someone must fail. But there comes a point.
Okay, we're going to do section 9.2 on differential equations with initial conditions. But we're actually going to start today by doing something different. Don't know if I've ever done this in any of these videos. I'm going to actually teach you something quickly that's completely not part of the lesson, related, but not part of the lesson. And the reason I'm doing this is to give you some context for next year, because we're not going to have time to talk about this too much. What I want to talk about is the difference between what we did last day, which were indefinite integrals, and something you'll be working with a lot next year at university, which are definite integrals. So indefinite integrals we did last day. Remember, it would be something like this. Let's say we have x squared plus x to the negative 2 dx. And we know how to solve this now, right? What we would do, we'd remember our rules for the indefinite integrals, which is also antiderivative. And in the first term here, we'd raise that 2 up to 3 and divide by that same amount, the 3. And for the next one, we'd raise that negative 2 up 1, which is negative 1, and we divide by the same thing, which is negative 1. And then we'd always remember to put plus c. If we simplify, you get x cubed over 3 minus, it's going to be x to the negative 1, so why don't we put it 1 over x plus c. And this would be our answer right here. This is the indefinite integral, or antiderivative, same thing. Now what I want to take a look at is what a definite integral is. So here's an example of one. X squared plus x to the negative 2 dx. Wait a minute, that's exactly the same thing as what I wrote here. But I'm going to add one thing, well actually two things. I'm going to put the number 2 up here. I'm going to put the number 1 down there. Okay, so now what we've done is we've been specific about the range that we're interested in with this integral. So what we would do is you'd start by taking the indefinite integral. You do exactly what we just did. So you'd end up with x cubed over 3 minus 1 over x plus c. And then I draw this line here. I don't really want to worry about the notation. And I put that 2 there and that 1 there. So what's the next thing you would do? You would plug the 2 into the x's and evaluate this amount. You'd plug the 1 into these x's and evaluate that amount. And then you subtract them. And you see what would happen with the c's if I did it once and then subtracted another c? They just disappear. So in fact, when you're dealing with definite integrals, you actually don't even need to worry about the c here. Okay? Again, I'm doing this fast. We're not going to do it this year. I just want to give you a sense of this. So what I would do again is I'd start by plugging 2 into the x's. So I would have 2 cubed over 3 minus 1 over 2. Then I would subtract plugging the 1 into the x's. So I'd have 1 cubed over 3 minus 1 over 1. So let's do that somewhat quickly. 2 cubed is 8 over 3 minus 1 half minus 1 over 3 minus, well, this is just 1. Okay, common denominator is 6. We'd have 16 sixes and 3 sixes. I subtract, I get 13 sixes. Minus 1/3 minus 3/3 is negative 2/3. This means add, and this would actually become 4 sixes plus the 13. So you get 17 over 6. That's our answer. Big deal, right? Why am I showing this? Who cares? It's just some weird thing. Because I want to show you what this actually means. What we've found is, if we were to draw this function, I'm going to show you what it looks like in just a second. If we were to draw this function right here, okay, maybe I'll go to it right now. Here it is. This is that function. And remember how our numbers that I included in the definite integral are 2 and 1? Right? This 2 and this 1 here. What this means, what this allows us to do, and this is incredibly powerful, this is why I wanted to show you. Remember how with derivatives we were learning about the slope of the tangent line and just how useful this was? Well, with definite integrals, what it allows you to find is the area under the curve. So from 1 to 2, if I go back, if I want to know the area under the curve, this curve right here, from 1 to 2 and down to the x-axis. So I don't think I can draw on this, unfortunately. Okay, boom, I just had a brilliant idea and screenshotted it. So if I wanted to know the area under this curve down to the x-axis from 1 to 2, right, those are our numbers there, 1 and 2, so that would be below here and everything in between up to the curve here. So in other words, all of this, if I wanted to know the curve, that'd be really hard to do without calculus. It'd be next to impossible. But we could do some of it, couldn't we? We could do this rectangle down here. I could tell how much this is the area of this, because for that rectangle right there, the area would be length times width. The width right here is 1, and the length, or the height if you want, is 1, 2. So for this green area right here, we have an area of 2. Plus, we'd have to add on this area here of this purple. We can't exactly do it, but we can get a sense. We could think of this as being a triangle, couldn't we? So for this triangle here, how high does it go? It goes up 1, 2, and a little bit. 2 and a little bit. And if we looked at this, so we have a base of 1 times a height of 2 point, well, I guess we could even do the point. It's 2.2, I think. And then, of course, you have to divide by 2. So you end up with 2.2 divided by 2 is 1.1. If you add 2 and 1.1, you get 3.1. Okay, what's this equal to? This is actually not equal to 3.1. This is equal to 2 and 5/6. But hey, 2 and 5/6 and 3 and 1/10, that's what this is. Those are pretty similar to each other. So we can get a sense by just using our formulas for rectangles and triangles, but to get exact, you need calculus. And that's what we found here. We have found the exact area underneath this curve from 1 to 2 above the x-axis. Now, if you were doing something that was a shape that went below the x-axis, this part below the x-axis would just be subtracted off of the area above. Okay, so again, we're not going to do that at all this year, but I just wanted to give you a sense because this is one of the most important parts of calculus, this idea of finding areas below curves, and it's so much related to our indefinite integrals. You actually start by doing an indefinite integral, and then you just plug in these numbers here to get the actual area. Pretty powerful and pretty cool. But that's not what we're doing today. What we're doing today are differential equations. So what are those? These are equations that involve derivatives of a function or functions. They're common in equations that describe the general laws of nature. So in nature, things aren't usually consistent, not constant, so there's often change involved. Differential equations often model those very well. And they often involve time-dependent processes where information is known about the initial instant, t equals 0. But it doesn't have to be the initial instant, it could be any instant. And we'll take a look at some of those too. Okay, so for example, so we're going to solve ds dt equals 2t. So when you took the derivative of s, so remember that's kind of like saying that s prime equals 2t, and we know what s equals. S is equal to 3 and t is equal to 0. So the first thing we want to do is we want to know, what does the function s look like? So what we can say is ds equals the antiderivative of 2t dt. So we've got to take the antiderivative of this. So we can do that without much difficulty. The 2 is just a coefficient. This t with a exponent of 1 is now going to go up to exponent of 2. And of course we also have to divide that by the same amount, 2, and we add our constant. So pretty easy to simplify. Cross out the 2's, you get t squared plus c. Now what does that equal? That's what s equals. Remember, we wanted to know what the s function looks like. This is what it looks like. So that's pretty great. We have the s function now. But we can even do better than that, because look, it gives us some information. It tells us that s equals 3 when t equals 0. So what do you think we do with those things? We're going to plug them in here. S equals 3 when t equals 0. We only have one unknown, which is c. If we solve this, we get 3 equals c. We now know what c is. So this was great when we figured out the s function like this, but now we can do even better and plug a number into c, which is 3. So our final answer would be s equals t squared plus 3. And that's the idea with differential equations. Let's try another one. Find the curve y equals capital F of x that passes through negative 1, 0 and satisfies dy dx equals 6x squared plus 6x. So again, this is like what y prime is. Y prime is 6x squared plus 6x. And what we want to know is, what's y equal to then? So we do the same sort of thing. We say dy equals antiderivative of 6x squared plus 6x dx. And now we have an antiderivative to find. So we're going to take the antiderivative now, so I can actually just write y here. Y equals, well, this raises by 1, and we divide by the same amount. This exponent here raises by 1, divide by the same amount, and we're left with a constant. So y is equal to, cancel or simplify, you get 2x cubed plus Simplify, 3x squared plus c. Great, we have the y function, but I'd love to know how much that c is, that constant is. We can do that because we know this information right here. Here's our x, here's our y. So when y is 0, we have an x value of -1 cubed plus -1 squared plus c. We only have one unknown, so we can solve this. 0 equals -1 cubed is -1 times 2 is -2. -1 squared is 1 times 3 is 3 plus c. So we get 0 equals 1 plus c, or c equals -1. Great, we go back up to here, we plug the -1 in here, and we'll have our answer. Y equals 2x cubed plus 3x squared minus 1. Okay, these are very similar. We can do this really quickly. This is what y prime equals. I just want to make sure you're clear what this dy dx, how it relates to everything. Our y prime is e to the negative x. We want to know what y is. How are we going to do that? If we know what the derivative is, and we want to go back to like the original, so to speak, we need to take the antiderivative. So you want to say dy equals the antiderivative of e to the negative x dx. So y is equal to, we're going to take the antiderivative now. Remember how to do it with e? You just write exactly the same thing, e to the negative x, but whatever the value is up front here, that's -1, you divide by that same amount. And we have our constant. So simplify that, y equals -e to the negative x plus c. Awesome. Now we want to figure out what the c is equal to, the constant. Well, it says it goes through the origin, so the y should be 0, and the x should be 0. Only one unknown, it's going to work. So 0 equals, -0 is just 0. E to the 0 is, well, anything to the 0 is 1. So we get -1 plus c, which means c is equal to +1. Go ahead and plug it in right here, and you'll have your answer. Y equals -e to the negative x plus 1. Okay, this one is difficult to picture. The line y equals 8x plus 2 is tangent to the graph of y equals f of x. Find f of x if f prime of x equals x cubed. Oh boy. Okay, so we have this line y equals 8x plus 2. There's a positive slope, so I'm just going to draw it like this. Y equals 8x plus 2. And then we have some function. I have no idea what it looks like, but I'll just draw it like this or something. And it's tangent at this point right here. So this is y equals f of x. So what we want to do is we want to find out what is this function here if f prime of x equals x cubed. So let's see some of the things we know. First of all, this graph right here, this blue line, what's the slope of that? That's an easy question. The slope of y equals 8x plus 2 is 8, right? It's a slope-intercept form, so this is our slope right there. Well, therefore, then if we were to find the tangent line of this, I know this is the tangent line, but what's another way we could find the tangent line of this function here? We could take f prime of x. So f prime of x must be equal to 8 as well. And it tells us right here that f prime of x is equal to x cubed. Well, we can easily solve that, can't we? Just take the cube root of both sides, you get that x is equal to 2. So what we now know is, if I was to draw my xy axis here, that this is at 2. This is when it's an x value of 2. And in fact, we can do better than that. We can find the y value here too, can't we? How come? We can use this blue equation right here. So the tangent point is equal to, or I'll put y equals 8 times x, which is 8 times 2 plus 2. So we get y is equal to 16 plus 2, y is equal to 18. So we now know that this point right here, this green point, that's the point 2, 18. So now we have what we want. We have a differential equation because we have our point, just like before we had point, like the origin up here. Remember in this question up here, it told us about the origin. It doesn't matter which point it is, but we do have one point, which is 218. And we also know how much the derivative is equal to. The derivative is equal to x cubed. Well, we can reverse engineer this, right? We can take that and do the antiderivative of that. So let's do that now. In order to get f of x, what we need to do is take the antiderivative of x cubed. Well, that's not too hard. The antiderivative of x cubed, we raise that 3 up to 4, divide by the same amount, and we add on the constant. And this is what f of x is equal to. Or y, if you'd rather put y. So now we can plug in the point we know. So we set up here our point is 218, x value, y value, or f of x, same as y, right? So we have 18 equals 2 to the 4th divided by 4 plus c. 18 equals 16 over 4 plus c. 18 equals 4 plus c. Move the 4 and subtract, you get c equals 14. And so finally we can write down our formula. We have f of x equals, remember we're using this one right here, x to the 4th over 4 plus 14. And this is our answer. Okay, now let's just make sure this is correct. I've drawn a couple things here. First of all, I have that line that we talked about, that y equals 8x plus 2, there it is, right? Goes through 2, that's the y-intercept, and it has a slope of 8, 1, 2, 3, 4, 5, 6, 7, 8 over 1, yep, perfect, that works. And then here's the graph, the function that we just discovered. This is our answer to the question we just did. We've said that this is our answer, this red one right there, there's the answer. And, well, it looks good, looks like they are tangent to each other. How can we really make sure it's true? Let's look at what happens at the point 218. So let's look at the tangent point, and I should find, oh look, it's showing it there in gray. Do you see it? When I get to that gray dot right there, boom, 218, absolutely. We've done exactly what we wanted to find. We found the function that has this tangent line, and they meet right each other at 218. Well done, class.
Yeah, say shoot, 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 baby. All you gotta do is say, shoo-ba-doo, shoo-ba-doo.